Okay, Saturday morning here. I get off there. I'm gonna go over the solution to M210 POD number 9. Let's see here. This is an optimization. Yeah, this is on optimization. And I'm going to do number 2. Because number 1's pretty standard stuff. Maybe I can do that one later. But number 2 is probably a little different. So let's do this. An island is 2 miles. Oh, God, I got allergies. An island is 2 miles due north of the closest point along a straight shoreline. A visitor is staying at a cabin on the shore that's 6 miles west of that point. The visitor is planning to go from the cabin to the island. Suppose the visitor runs at a rate of 8 miles per hour and swims at a rate of 3 miles per hour. How far should the visitor run before swimming to minimize the time it takes to reach the island? All right. Step 1 is always to draw a picture. So we have a straight shoreline. We have an island out here, which is 2 miles. 2 miles to shore. And then it says there's a cabin 6 miles west of there. So down here is a cabin where you're staying. And it is 6 miles west. Okay. And so you're going to run and swim. So you take off. You take off from here, going this way, and you're going to run along the beach here to some point, and then you're going to swim out to the island here like that. And the idea is to what? Minimize the time. Okay, so let's write down our function. It's actually going to be a function, and it always starts off as a function of 2 variables usually, which we'll call, I don't know, x and something, x and z. So the distance you swim is z, and the distance you run is going to be x, like that. Okay. So let's write down our variables. We just did. So x is distance run in miles, and z is distance swam in miles. All right, and this distance from here to here, from there to there, is 6 minus x. It also tells you that x lies between 0 and 6, because that's going to be the longest. Okay. So this is interesting because we're minimizing time. And remember, the units here, this is really important. Keep track of your units on these optimization problems and related rates. Okay, so let's do this. So t of xz is going to be, so you go 8 miles per hour times what? X miles? No. And so here's the trick with this problem. So if I did this, which is what you probably want to do, go 8 times x plus 3 times z, this gives you miles squared per hour. And over here you're going to get miles squared per hour, right? Because z is a mile and 3 is miles per hour. So you don't want that. Right? Remember, the distance traveled is your rate times time, and we want time. So time is distance over the rate. Okay, we want time units. So what we have here is distance, which is x miles. Let me rewrite this down here. Over 8 miles per hour. Plus the distance swum is z miles over 3 miles per hour. And you see, when you flip this around, because remember, when you divide by a fraction, you multiply by its reciprocal. This is hours over 8 miles, and this is z miles times hours over 3 miles. You see, these miles cancel out here, and you're left with what we want, which is x over 8 plus z over 3 hours. Right. So if you did this problem and it was started with 8 times x plus z times 3, it wouldn't work out. You'd get a negative answer for the final, I think. All right, so now we have our function, and it's in the proper form, x over 8 plus z over 3. The next step in this game is to eliminate z using the constraint equation. And what is that? That comes from this right triangle up here, and we use Pythagoras. So here's the constraint equation. So z squared equals 6 minus x squared plus 4. Solving for z, we get this little bit of ugliness, but there it is. Okay, and now we take this guy, what do? We stuff it in here, and the function is now in its form x over 8 plus this thing, over 3, and it's a function of x only. Okay, so getting to here is always the hardest part, and now the machine kicks in. We're just minimizing this function. All right, take the derivative. So what is it? So we do the chain rule, so it's 1/2 to the minus a half times the derivative of what's inside, which is 2 times 6 minus x, times the derivative of what's inside that, which is minus 1. Chain rule embedded, so twice. So power and chain rules here. All right, let's clean this thing up. Get it into a form that is edible. And don't forget this minus 1, it's key. So now we have 1/8 minus 6 minus x is on top, and downstairs I have a 3, and then this thing to the 1/2, right? Okay, we'll set this equal to 0 because we're looking for critical points. And find a common denominator, which is what? 8 times 3 times that thing. So that's 24 times 6 minus x squared plus 4 to the 1/2. All right, so what do I get on top here? You just cross multiply. So you get 3 minus 8. Okay, just cross multiply there, and the fraction can only equal 0 if the numerator equals 0. So this says 3 times this guy. Okay. And thankfully that negative is there, so we isolate the square root here, which is what this is. Right? And then square both sides. That kills the radical. So this is 9 times this guy now, but there's no radical. And this is 64 times 6 minus x quantity squared. Right? So squared both sides of the equation. That killed the radical. Okay, distribute the 9. Okay, bring this guy over here by subtracting, so we get 36 equals 64 minus 9 is the 55 times 6 minus x squared. Getting closer. Divide both sides by 55. Getting closer. Take the square root of this guy and solve for x is 6 minus the square root of 36 over 55. The positive root goes away because it's bigger than 6. And so there's our only critical point. Oh man. And so at the beginning of this problem, I should have put a little note that the square root of 36 over 55 is around, what is it, 0.881 or something? Yeah. So I would have put this at the top of the problem had I done this sucker beforehand. And so x is equal to 6 minus that, which is 5.19 miles, approximately. And so that answers the question. How far would you run? You would run 5.19 miles and then start swimming. Probably a couple more miles to go. That's a good workout. It's a Pullman workout. Tough to get back though. You'd be pretty tired. All right, that's a great problem. This is totally test level stuff. So, hope that helps.